Welcome, concrete super freaks. Today, I'm talking about moisture corrections. Yeah, moisture corrections. This is actually one of the most misunderstood topics in concrete mix design. This is a reason why a lot of people have challenges and problems every day producing consistent concrete. And if you can learn how to do it, you'll become super valuable. Aggregates are porous materials. They're also stored outside. So they get rained on and the wind blows on them, sun beats on them. So they're always changing in moisture on the inside and on the outside. And if you don't understand the moisture content of your aggregates, it's extremely hard to produce consistent concrete. What do I mean? Let's draw some pictures. So let's start out with two ideal, mythical situations. They don't happen except for in the lab or in our mind, okay? The first one is oven dry. Well, let me explain this picture first. This is an aggregate. It's supposed to be an aggregate. And this is supposed to be, if I could zoom way in and see what the inside pores look like, okay? That's what they look like. In this aggregate, there is no water on the outside because the shaded stuff is water. Okay, that's supposed to be water down there. There's no water on the outside and there's no water on the inside. This one has internal pores. It has no water. On the outside pores, it has no water at all. Outside surface. This is an oven dry aggregate. Oven dry. Only happens in the lab. Now, this is another mythical situation. This is like the mythical saturated surface dry. I mean, it's truly a unicorn. It's truly something crazy, imaginary in the world of concrete. But we can make it happen in the lab. This is when we perfectly fill every single internal pore. All the internal pores here are saturated. And there's no outside water out on the outside, none. No outside water. And we'll talk about how to make this happen. But this is known as SSD, saturated surface dry. Crazy important aggregate moisture content because inside a concrete mixture, inside the mixer, the aggregates are going to get to this place. That's why it's so important. And that's why we use this moisture content to design our concrete mixtures. We design them to be at SSD because in the mixer, they will be at saturated surface dry. But if you were just to go pick some aggregates up, you might find some that may be below SSD, maybe on a dry summer hot day. Okay, they might be that if you used a microscope and you looked inside, you would say the internal pores are like only partially filled. Partially saturated, we'll say. And let's say there's no water on the outside. Now, this is below SSD, right? This is below SSD, below. The moisture content is lower than saturated surface dry. It's somewhere in between these top two mythical places. Okay, that's one possibility. Here's another possibility. This one I say is above SSD. The internal pores are only partly filled. Okay, partially saturated internal pores. And the outside, look at that. It's like covered in water. It's got water going all the way around the outside. So it's just full of water. Maybe it's saturated on the outside. There's water sitting on the outside of it, all around the outside. So if the pores are partially filled and the outside is totally filled, hopefully you could kind of get this idea that this may be above SSD. It may be above this mystical place. You may be actually over here in the saturation continuum. And then you could have a situation where all of your pores on the inside are full. Full, full, full. It's totally saturated pores on the inside. But then there's still water on the outside. There's extra water. It's partially saturated on the outside. And again, this would put you above SSD. This would put you over here on the moisture continuum, right? If this is dry, this is SSD. You can go above SSD. You can go below SSD. You can never go below oven dry, though. I guess my point in doing all this is to let you know, and hopefully you can conceptualize how you can have different aggregates that are at different moisture states inside your concrete. But regardless of this moisture content, we've got to correct for it. Because in these situations where we're above SSD, we're actually going to be adding more water to the concrete. And these situations that were below SSD, we're actually going to be taking water out of the concrete mixture. And we've got to get this kind of tug of war, this kind of back and forth just right to get our water to cement ratio correct and keep our workability constant. That's a key in providing consistent concrete. So as I was saying, regardless of the initial moisture content, we've got to get this right. Once we dump this aggregate inside a concrete mixture, the pores are going to fill over time and they will become saturated. This is in a concrete mixture. Our aggregate will reach SSD, saturated surface dry. Now, it may take a little while. It may take it 30 minutes. That may be why right out of the mixer, you may have a pretty high slump, okay? And then over time, that slump may go down, down, down really rapidly. It may be those aggregates sucking up the water out of the concrete mixture, okay? But if there's extra water on the surface of the aggregates, then this has to be accounted for in the mixing water. And this might seem complicated. This might seem like really strange. A lot of people overthink this. They think in a very, very detailed way of like how to do this. There's a very systematic process, and I recommend you stick to that process. But it's not that bad if you design your concrete mixture to use SSD batch weights, because that's what they're going to eventually have. For example, let's talk about how this kind of works. Let's just say I have 100 pounds of rock, but it's above SSD. That means I don't really just have 100 pounds of rock. I have rock that is at SSD, and then I have some extra surface water that's coming along for the ride. And my batch water must be reduced to account for this extra surface water. Now let's say I have the opposite scenario. If I have 100 pounds of rock that's below SSD, so that means I theoretically have rock that's missing water, and it will steal that water. That's why it's a minus sign. It will steal the water from the concrete mixture to get inside the pores over time. And again, our batch water, we have to add batch water to account for this. And one of these could be happening in the rock and another one could be happening in the sand. That's why you have to pay attention. So to account for this, we have to look at the moisture content in the aggregate by measuring the current moisture content, and also to find the total potential moisture content, total amount of water the aggregate could absorb versus where it's at right now. To do all this, we calculate two terms. The first term is called the absorption capacity, and it's described by ASTM C127. This is the weight percentage of water that an aggregate can absorb in its pores. This is like the total potential amount of water that can infiltrate inside the pores inside the aggregate. So how do you do this? Well, this test's pretty straightforward. You take aggregate, you place it in a bucket of water, and you let it sit there, usually for at least 24 hours. Then you take the aggregate out, and I'm trying to show them shaded here because the idea is that that aggregate is wet on the inside, and then you dry it off with a towel. You dry it off to try to get all of the moisture off the surface. And this is theoretically the SSD weight. This is theoretically the perfect, mythical, unicorn weight that we want to make concrete. Then we cook the aggregate in an oven, and then we take the weight again. And this is what's called the oven dry weight. So to find the absorption capacity, we take the SSD weight minus the oven dry weight, divided by the oven dry weight, multiplied by 100. This value is typically between 0.3% and 1%, typically. Now it can change, but typically the absorption numbers are between 0.3 and 1. And you can get aggregates that have much higher absorption, up to 4%. And these can be plenty great inside concrete. You really just need to evaluate the aggregate itself. And then you also find the current moisture content. Now I want to make this clear that you can make concrete with any moisture content. You can make concrete with oven dry rock. You can make it with SSD rock. You can make it with above SSD, below SSD. You can make it with whatever you want. Okay? So don't think you can't, because you can. You just need to figure out the moisture content. And this is the current weight percentage of the water in the aggregates. This is the current percentage of water in the aggregate in terms of the oven dry weight. This is described by ASTM C 566. So the way you do this is you take a stockpile. That's your sample weight. You take a scoop, maybe about 1,000 grams or so, and then you cook the aggregates in an oven, okay? And then you take the weight again. This is called the oven dry weight, and this is called the sample weight. You plug in this simple equation. The sample weight minus the oven dry weight divided by the oven dry weight multiplied by 100 gives you your moisture content in terms of percent. And this number is usually below 3%. Usually. It can be higher, especially if your aggregate's a higher absorption aggregate. But usually it's less than 3%. So, if your moisture content is greater than your absorption capacity, that means your aggregate's above SSD. That means that water needs to be taken out of the mixture. Above SSD, above where we designed, we've got to take water out. If your moisture content is less than your absorption capacity, then that means your aggregate's below SSD. And again, water now needs to be added to the mixture. Now, there's nothing again wrong with having an aggregate that's above or below SSD. It doesn't matter. We can correct for this. It's okay. We got this. And if it so happens that the moisture content is equal to the absorption capacity, then no change is needed at all, and this is extremely rare. But it happens sometimes. So how do we make these corrections? How do we really earn the money here? Well, you compare the measured content to the SSD value and you adjust your batch weights. Yeah, easier said than done, right? Here's a tip, and I'm going to bring this up again, but this is a really important tip. Whatever weight you change your aggregates by, you have to do the opposites to your water. We're going to actually find out that sometimes you may adjust a mixture. You may take out some aggregates for one reason, because you're above SSD, for example, and then you have to add some water back in. I'll explain that to you coming up. So let's derive an equation to help us do this, to help make this happen. So let's start out with a basic statement that would hopefully everyone would agree to. The SSD aggregate weight, this is the weight of a perfect SSD aggregate, is equal to the oven dry aggregate weight, the pure dry aggregate, plus the water needed to fill the pores. That's just the definition of an SSD aggregate, right? So I'm going to change this number, this water to fill the pores, and I'm going to change it to the oven dry weight multiplied by the absorption over 100. And if you go back and look at the equation that we talked about before, you would realize that this is equal. The water to fill the pores is equal to the absorption divided by 100 multiplied by the oven dry aggregate weight. Now I can factor out oven dry aggregate weights from both these. can pull it out. And this turns into a 1, and this turns into just absorption over 100. So SSD aggregate weight equals oven dry aggregate weight times 1 plus absorption over 100. Now, I can actually do a little bit of algebra. I can divide by this term over here and get oven dry aggregate weight is equal to SSD aggregate weight over 1 plus the absorption divided by 100. And this is what we're going to call equation 1. And we're going to need this. We're going to solve another equation in terms of aggregate dry oven weight in just a second. And we're going to need this to sub into it. Okay, let's keep going. Now we're going to take another equation, hopefully it makes sense. The actual moisture content. This is what we call like the sample weight. This is the actual moisture content of the aggregates. Again, would be equal to this oven dry aggregate weight plus the water in or on top of the aggregate. This is kind of the extra water. So again, we can go back to the definition of moisture content that we derived before. And this is the oven dry aggregate weight is multiplied by the moisture content over 100. Again, if you don't follow this, go back and look at the previous equation that we talked about. To find the moisture content, it's the oven dry weight multiplied by the moisture content over 100. This gives us the water, the extra water that's in or on top of the aggregate. Now here, I can factor out oven dry from this, and I get 1 plus moisture content over 100, and this is called equation number 2. Now, if I plug in equation number 1, this is what I solved for on the previous page. If I plug in here and multiply by this, I'll get the SSD aggregate weight multiplied by this funny thing. And this gives me my actual moisture aggregate weight. And again, my actual aggregate moisture weight is going to be equal to this, and I've just multiplied by 100 on the top and 100 on the bottom. That's easy. Multiplying by 100 over 100, so just like multiplying by 1, it's not that big of a deal. So I multiply by 100 on both of these. This is just to make the calculations easier. If you don't believe me, these two equations are equivalent, mathematically equivalent to one another. And this is just to make that calculation easy. Note, to do this, the moisture content and the absorption that you plug in with has to be used in terms of percent. So if your moisture content was 3.2%, then you're going to use 3.2 in this calculation. Okay, 3.2. You don't put the percent sign in. The hundreds have already been taken care of for you. And this ratio is going to correct from the SSD batch weight to account for the moisture content of our aggregates. This is the secret. And this number, if it's less than 1, then that means your aggregate is less than SSD. And that means we're going to have to add water to the mix. And if the number is greater than 1, then that means the aggregate's greater than SSD. And that means we're going to have to remove water from the mix. Now, these are really important points. This is an idea that if I weighed out a certain amount of aggregate that has this factor to be less than 1, then that means I weighed out aggregate that wasn't at SSD. So I've weighed out too much aggregate. And I'm going to have to take a little bit out of my mix. And I'm going to have to add water in. And if this number is greater than 1, this factor is greater than 1, that means my aggregate's greater than SSD. That means extra water was coming along for the ride. And I didn't weigh out enough aggregate. I didn't get enough. I got water instead. So in this case, I'm going to have to add aggregate back into the mix. And I'm going to have to take out water. And again, this calculation is going to help me do this. Remember, the mass of aggregate you add or remove is equal to the mass of water you remove or add. Why did I do this? Why did I do one add, remove, and the other one remove/add? It's because if you add aggregate, you're going to be removing water. And if you remove aggregate, you're going to have to add water. Because again, when you weighed it out, you weighed out either extra water and you weighed out extra aggregates, and you have to correct for that. And hopefully this will all make more sense after we work an example together. We'll do that next time. Thanks.